Early 1945, cold seas off Japan. An American F4U Corsair ditches after engine failure. The pilot bails out. The fighter stays afloat just long enough for Japanese patrol boats to arrive. They pull a nearly intact Corsair from the water. For Japan's engineers, it is a rare gift. A chance to study the machine that had humbled them in the skies. For 3 years, Japanese pilots had met the Corsair from the Solomons to the Philippines and now over the home islands. They knew its speed, its punch, its toughness. But they had never handled a complete example. Now they could measure, weigh, and test. They could see, part by part, how far American industry had marched ahead. The Corsair was born from an audacious brief. In 1938, the United States Navy asked for a carrier fighter that could break 400 miles per hour, yet land slow, carry heavy guns, and fly far. Chance Vaught's team built around the biggest engine they could get, the Pratt & Whitney R 2800 Double Wasp. 18 cylinders, 2 rows, 2,000 horsepower. A giant propeller demanded the inverted gull wing. Shorter landing gear, proper prop clearance, less drag. Bold ideas turned into a distinctive silhouette. By early 1943, the Corsair was in combat. Its debut was rough. Japanese defenders, skilled and coordinated, punished early mistakes. American pilots adapted. They learned boom and zoom. Do not turn with a zero. Hit hard from altitude. Use the dive. Climb away under power. Second Lieutenant Kenneth Walsh of VMF 124 mastered the technique and became the first Corsair ace. The salvaged fighter went to the Navy's Yokosuka Naval Air Technical Arsenal. The Army's Institute at Tachikawa sent specialists too. They began with photography and careful measurement. Wings, fuselage, landing gear geometry. The inverted gull wing impressed them. So did the complexity. Those compound curves and precise angles demanded first-rate tooling and jigs. Achievable in American factories. Harder in Japan by 1945. Then a surprise. Fabric skinning aft of the main spar in portions of the outer wing. Fabric on ailerons, elevators, and rudder. Not a shortcut, but a choice. Save weight where loads are low. Save aluminum for the places that carry the fight. The fabric was sealed and doped to resist weather. Light where it could be. Strong where it must be. A lesson in disciplined design. Inside the wing, the main spar told the bigger story. A large, high-quality aluminum alloy forging. Uniform grain. Excellent heat treatment. High load capacity. Ribs, stamped in dies, came out nearly identical, part after part. That consistency said as much as any speed figure. It spoke to gauge blocks, inspection regimes, and workforce training. In Japanese plants under bombing and shortage, such repeatability was slipping away. Armament followed the same pattern. 6 Browning M250 caliber machine guns. Tight installations, clean feed chutes, reliable charging and ejection. Ammunition boxes integrated as a system, not as add-ons. The guns themselves showed polished machining and exact tolerances across serials. American ordnance factories had reached a steady state of mass precision. Protection mattered too. Around 150 pounds of armor plate guarded the cockpit. Bullet-resistant glass, roughly 1 1/2 inches thick, sat ahead of the pilot. Self-sealing tanks layered with rubber compounds swelled when pierced. Fire risk dropped. Range and survivability rose. Japanese fighters had often traded protection for agility. The Corsair proved that power could buy both speed and protection, if the engine and airframe were designed for it. At the center was the Pratt & Whitney R 2800. Two-stage supercharging, tight clearances, fine surface finishes on pistons, rods, and gears. The engine did what it promised for long hours between overhauls. Not just theory, practice repeated across thousands of engines. The Hamilton Standard hydromatic propeller, 13 feet and a few inches in diameter, changed pitch smoothly under hydraulic control. Large, efficient blades demanded exact metallurgical control and careful balancing. Everywhere the Japanese team looked, they found the same signature. Wiring looms neatly routed, instruments clear and numerous, landing gear robust with positive locks, surface finishes smooth, fasteners consistent, materials that behaved the same from one part to the next. Not a single miracle part. A whole ecosystem working together. Context sharpened the verdict. By 1945, Japan was short of aluminum, high-octane fuel, bearings, and skilled labor. Air raids scattered production. Quality control bent under pressure. The Corsair laid out what an uninterrupted industrial base could achieve. After the war, American teams found reports, photos, and even patched Allied aircraft at Yokosuka. The Japanese assessments were precise, professional, and plain. The gap was real. It was systemic. It would take years, not months, to close. In combat, the Corsair posted an official kill ratio near 11-to-1 against Japanese aircraft. That number reflected more than one design. It reflected training, logistics, and a production machine that delivered the same standard over and over. The captured Corsair did more than answer technical questions. It became a mirror. It showed Japan's engineers what consistent metallurgy, rigorous tooling, and disciplined process control could deliver. Those lessons, painful at first, helped shape the post-war focus on precision, quality, and continuous improvement. A defeated nation took notes and rebuilt.